Hey everyone, today we're going to be talking about vectors and what vectors look like on a plane. Now, I said it before when we were in chapter 5, and I'll say it again. Most students that I've dealt with so far, and even my own personal experience, have found that vectors are a much simpler concept to grasp and much easier to work with than things like proofs and all of that. So if you were struggling in the past chapter, really give a fresh start to this chapter. I think things will come really rather naturally, if at least maybe not naturally, but they'll come a lot more smoothly than they were in previous chapters. So let's start off with some basic ideas. And right now I'm going to talk about a very what's called a paradigm shift. I'm going to try to shift your entire way of thinking for a second, add a whole new set of understandings. Let's start with the idea of numbers and what we know numbers are. We've got a lot of numbers. We've got the whole numbers and the natural numbers and the integers. We've got the rational numbers, all which encompass all those numbers. We've got the irrational numbers that are all the other numbers. Let's write some of these down. We've got 1, 2. We got the counting numbers. We've got 3/4. We've got pi. That's an irrational number. But we've got the real numbers that account for all of those. We've got imaginary numbers like I. But what I want you to understand right now is that all the numbers we've dealt with, we just called them numbers. Like, these are the numbers. But they're actually a special type of number. We've called them numbers the entire time, but what they really are officially called are scalars. They have some discrete, definitive value to them. Every single number we've dealt with so far is called a scalar. So let's start with that understanding. Everything we've worked with, just every number from 2 to pi to e to 3i pi, they're all scalars because they consider some sort of left to right quantity, some sort of value on the x-axis. I can have 4 apples. I can have, in theory, I apples. That is something that's technically possible, sort of. Or you can have I volts or something. But so everything is everything we've dealt with so far is scalars. A whole different kind of number or a whole different kind of way of thinking, in a sense, is vectors. Vectors are not just a size, so not just a magnitude, they're not just a length, they're not just something like, I've got something that's a size, that's a size 3, but it also has an extra element to it of a direction and a magnitude. The magnitude tells you just really what the scalar is, how big is this thing, and the direction says which way is it pointing. So if you had, for example, had a number, if you had normally a scalar could be something from here to here. That's a value of, and maybe it's a size of 3. A vector would say it starts at some point, say right here, and it ends at another point, say way up here, and it's got a size of maybe 4. And so we go from the beginning. This is the end. The top part is the end. That's what not necessarily, but I'm just calling it that. And we're going to say it's a size of 4. So basically what we've done is we've taken a size, we've taken a quantity, and we said, let's put it on a 2-dimensional plane. Let's put it on a graph and see how that looks. And that's all we've done. So we could have taken 3 and done that as well. We could have taken a 3 and we could have said, I'll put the 3 way over here. And this will be 3 big. It's the size of 3, but I'm going to put it right here on the graph. I've turned it and I've pointed downwards, kind of downwards. And that's all a vector is. It's a scalar. It's a number. It's a size. It's something, but it's just situated on a plane, so it's got some sort of direction to it. If that's all too confusing, just think of it. It's a magnitude. It's a size, and it's a direction. It's going some sort of direction. To put it another way, there are let's kind of look at 2 different ways of writing a vector. Maybe they'll make it a little bit clearer. So if I could take a vector, we could say this 4 over here that we've been looking at, this 4 starts in the, what the point does that start at? It starts in the point, let's say 1, 1. That's 1, 1. And it ends in the point, that's 3, 4, or 3, 5. So it ends at the point 3, 5. And so we'd say this is an arrow, this is a vector that starts at the point 1, 1 and goes to the point 3, 5. So we could actually write it as, if we want to write this as a vector, what it means, we could say, let's get rid of all this extra junk down here. Stop, make it clear. This will make it clear. We'll say this vector, we'll call the vector, I don't know, let's say vector G. And we use a little arrow on the top to say that's what the vector is called. This is called vector G now, because it's got a G, it's got a capital G, it's got an arrow on top. That means we're dealing with vector G. And we're going to say it goes from point, let's say 1, 1 is point A, and let's say 3, 5 is point B. Okay, so we'll say vector G goes from point A to point B. Okay, so notice I've done here. I said this first one with just one number says this is the vector, the name of the vector. So if there's only one letter involved, that's the name of the vector. If there's two letters involved like this, that's what we're saying here, is that we've got a vector, and here are the start and end points. This is the start point and end points. So what we're saying is the vector G that we just defined is the vector from point A to point B. That's all we're saying here. Okay, and now we need to say what point A and point B are. So we'll say that point A, we'll say A equals 1, 1, and B equals 3, 5. In other words, we're saying when we use an initial point and a terminal point, the beginning, or another way to call it is a beginning point and an ending point to write it, we're saying a vector starts from that initial point, 1, 1, and goes to that end point, 3, 5. That's all we're saying. So you draw the beginning, you draw the end, and you draw that. Let's look at one other one. Let's say we wanted to say a point started at the value, let's say we'll say make a vector that starts at the value 0, 0, and let's say it goes to the value, let's say 2, 4. So it goes from 0, 0 to 2, 4. In fact, let me use a different color just so it's clear that we're using a different vector now. From 0, 0 to 2, 4. This is going to be our orange vector. And let's say this is a vector. Let's call this vector Q, because Q is a cool letter. So we'll call this vector Q. And so we've got our one point is 0, 0. And we'll call another point 2, 4. And let's give some names to these points. Let's say point 0, 0 is point, I don't know, let's give some random letter. How about C? And 2, 4 is, let's call that point D. It doesn't matter what letters I chose, I just chose some random letters. Okay, so we'll say that this is, that Q equals, the vector Q equals from point C to point D, which is the same as saying, or that it is the value of, it's a point from C to point D, it's the vector from point C to point D, where C equals 0, 0, and D equals 2, 4. Okay, so that's what it looks like when we're using a beginning point and an ending point, an initial point and a terminal point. That's what that's all about. But sometimes, a lot of the times, in fact, many times, sometimes even in certain cases, most of the times, nearly all the times, the actual vector itself usually starts at 0, 0. A whole lot of the time, that initial value ends up becoming 0, and we use 0, 0, 0, that origin, a whole ton when making these things. So to make that simple for ourselves, we said, mathematicians said, well, instead of just writing this same thing over and over and over and over again, the same terminology, let's try to make a shorthand for it so we know what we're talking about. And he said, okay, we'll make this new form called component form. And he said, in component form, we're going to make it really simple. We're going to write a whole new kind of terminology. And in component form, let's use orange as well. We'll say, instead of writing, if we're going to start from the point 0, 0, and make our initial point 0, 0, like we did in this orange vector, Q, the vector Q, we could write it in a different way that makes it a whole lot faster. Instead of writing C to D and defining what C is and defining what D is, let's just say that vector Q is the same as this. We're going to write like a less than sign, and then 2, comma 4, and then a greater than sign. Or maybe a little elongated, but it looks kind of like this. And this is just really fancy math speak just to say, hey, it means to say exactly what it says above. We've got a point that starts at 0, we got a vector that starts at 0.00 and goes to 0.24. So this is, the first one is initial and terminal. And the second one is what's called component form. And remember, the component form only works if the initial point, let me underscore that so that's clear. The initial point needs to be 0, 0. And if that's the case, you can make a component form. And it's just implying, it's saying if you have two things, it'll start at 0, 0 and go to that point. Okay, so we've talked about a couple things so far. We've talked about how a vector is different from a scalar, of all the numbers that we're used to. We've talked about how an initial point and terminal points is a way to write a vector, and we could talk about how component form is another way to write a vector if it starts at 0, 0. The next thing we can talk about is equivalent vectors. What we're really talking about here is that, well, oftentimes, let me state it again. The definition of vector is all it needs to be in order to be a vector is to have direction and magnitude. And we only really think about, most of the time, its direction and magnitude. It doesn't matter where it is on the graph, as long as it goes in the same direction and has the same size. It's basically the same vector. Here's what I'm trying to tell you. Let's say I had a vector that went from, let's say, 0, 1 to say 2, 3. Let's draw a little line here, and let's draw a little vector there. And let's say that vector, I don't know, I could use the Pythagorean theorem to figure that out, and you could probably do it in your head better than I can. But let's say the size of this is about square 3. Yeah. No, 1 squared. No, this would be, if we drew a little triangle here, this would be, let's see, that'd be 2, 2, and 1 squared. Square root of 2 times 2. Okay, so that would mean, I just did the Pythagorean theorem real quick right there. All I'm saying is that this side here, the size is 2 times the square root of 2. Okay, I'll go into that a little bit more later. But 2 times the square root of 2 is the size of the vector. Now let's say we moved it a little bit. Let's say we brought it down and put it over, let's say down over here. We start at this point and go to this point. The size is still 2 times the square root of 2. I hope I got that right. That number right for magnitude. and because the size is still the same, it points in the same direction. You can see this is like a 45-degree angle, 45 degrees, and this is like a 45-degree angle. So they both point in the same direction, they have the same size. So we call these are equivalent vectors. They're basically the same. They have the same direction, have the same magnitude, and I think it's the same direction, magnitude, they're the same thing. So these two are called equivalents. Now, how can we tell if a vector is equivalent? Sometimes you're not really given much about a vector, but you still want to figure out if it is equivalent. So we can figure out whether they're equivalent in a couple of different ways. Let's look a little bit about what these two vectors are. I'll use let's say red for the first one, and let's say the first one is vector v, and let's say the second one, I'll use this dark blue for it, or whatever this is, and this is vector, I don't know, x. That's vector x. And let's say so vector v is the same as let's say it's got points a and b, and vector x has points c and d. I'm just naming some points here. And let's say vector v goes from a to b, and its points are, let's see, a, let's try to be accurate here, that's 0, 1, and b is the points, let's say it's 3, that's 2, 3. Okay, and for vector x is the vector from c to d, and it's got where c is, let's see, that's a value of, let's count it out. That's 1, 2, 3, 4. That'd be 4, negative 3. And then we go all the way to D, which is 6, negative 1. Okay. So the question is, we want to figure out if we weren't given the graph and we couldn't see that they were equivalent, or it was kind of foggy, we weren't entirely sure, we want to figure out if they're equivalent. One of the ways we can do this is by seeing if we can add numbers, add and subtract numbers from the x and y coordinates to figure out if they're the same. Think about it this way. I think the notes here will help you with that, help you kind of see it. If you can translate a vector, let's put it this way. Because the vectors are the same, let's neglect the notes for a second. If you can take the arrow and you can translate it up or down or left and right on the graph to get to the other vector, then it's the same. So if I could translate A to get to C and translate B to get to D, and do that without changing the distance between A and B and the distance between C and D, then I can make an equivalent vector. Here's an easy way to do that. If I want to move A and B right, if I want to move this vector, let's say I want to prove that they're the same vector, so I can move them right. I can move A and B right. Let's see, I need to line A and B up with C and D. If I want to move it right, I want to move them right, let's say about 4, because A is currently at 0, and I want to move it to 4. Or on the right side, you can say that A equals 0, 1, and C equals 4, negative 3. I want to move it to the right by 4 to get it. So I want to add 4 to the x. Add 4 to the x. I'm going to add 4 to the x here. And I'll just add 4 to, actually I won't add 4 to the x's in the bottom. I want to leave the second one alone. I'll add 4 to the x's of A and B. And that gives us the points, let's say 4, 1, and let's see, 6, 3. Okay, so I added 4 to the x, and that gives me this vector here. That gives me this. If we graph that. Okay, so then the first part of translation, I've moved it to the right by 4, and you can see it's kind of lining up a little bit. So I've translated 4 to the right. Is basically what I've done with this vector. I can translate a vector up or down, left or right, any way I want to by adding the same number, adding in any number I want to either to both x's or both y's. If I add any number I want to both x's or both y's at the same time, it'll be a proper and good translation. It'll work out. In the same way that if I wanted to move an equation up or down, like y equals x squared plus 2, I could add some number to the whole equation to move it up or down. In the same way, if I want to move a vector left or up or down, I could add some number to the y coordinates. Whatever the y coordinates are, I can just add some number to both of those, and I'll move that up and down. So if I want to move for the y, this new translated yellow vector, I want to move that down to CD. So what I'll do is, let's see, the yellow vector is how many above? It's about 4 units above the second vector. So I'm going to subtract. Let's say I'll use this green one and subtract 4 from y. Is that right? Yeah, I should subtract 4 from y. From y minus 4 from y, and that'll give me the points. That'll be 4, negative 3, and that'll give me the points 6. No, that'll give me 6, negative 1. All right, and I'll bring that down. So 4 negative, bring that down 4, 1, 2, 3, 4. 4 negative 3 is there. 6 negative 1 is there. That gives us this green vector, which is the same. Okay. Oh, you see the points are the same too. So this equals the green and the purple equal each other, the same vector. So by doing this, I was able to realize if I translate a vector up or down or left or right enough to match up the numbers. So let's say A and B now equal C and D. The coordinates of the green vector equal the coordinates of the purple vector. Because I was able to make them exactly the same, it all works out. It means that they are equivalent. They are now equivalent vectors. Okay. If that's still confusing, feel free to come contact me. I want to help you out and make sure that this gets solidified in your head. There are two other types of vectors. Well, there's two special types of vectors that are very unique, and we like to give them special names. One of them is the zero vector. The zero vector, what's special about that is that it can go any direction you want to. It can go up, down, left, or right, or any direction at any angle, but it just has a magnitude of 0. So if you think about a zero vector, it has its size is 0, so it can be an arrow or something, but it's not really going to move much from the point. It's just stuck there because its size is 0. A unit vector, on the other hand, this is 0. And a way to kind of think about it is a zero vector is really just a point. It can be pointed in a certain direction. It's a point that has a direction to it, but it's really just a point because it has no size to it. Okay, so a unit vector might be somewhat analogous to a unit circle. It's the same thing as any other vector, except its magnitude is a unit, 1. So if we have a vector that goes in this direction, let's say its magnitude is 1, that's a unit vector. Okay, finally, that's all there is to those. And finally, we have the magnitude of vectors. If you want to find the magnitude of a vector, we can use a pretty fancy, the fancy way of explaining it is through the Pythagorean theorem. And you'll notice that this formula down here looks a lot like the Pythagorean theorem. So if you want to find the size, the distance between 2 points, remember the distance formula? We use the Pythagorean theorem to find the distance formula. Let's say I want to find the distance between this point and this point. Or, yeah, we'll say that. This is 1, 1, and 2, 3. That's what those points are. And I want to find the distance between these 2 points. Well, I'll use the distance formula. I would say the distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And if you're having trouble remembering that, that's just the same thing as the Pythagorean theorem. You can start with the distance between 2 points, as saying the change in x. This is the change in x. This is the change in y. Change in y. Change in x. And we say it's the change in x squared plus the change in y squared. That is a distance formula. And the square root of all of that. And because we know that creates this distance. That distance equals the change in x squared plus the change in y squared equals, we know that x squared, that change in x squared plus the change in y squared equals the distance squared. Because that comes out of the Pythagorean theorem. If you square both sides, then you will get exactly this formula. The square root of change in x, the square root of change in x plus square root of change in y squared equals a distance. Okay, so that's the distance formula. The magnitude formula is exactly the same as the distance formula, but you just got to remember one thing. We'll get to that in a second. Before we get into that one thing, you might want to notice that the reason why it still works, why it's the same distance formula, because you're trying to figure out the size of an arrow. I want to figure out the size of this vector, and I know what the points are. So I'm going to find the change in x, x2 minus x1, and the change in y, y2 minus y1. And I'll just put that in distance, and I'll find out just how long that distance is, or how big that vector is. And so that's how we get the vector form, the distance formula for a vector. Now you might notice something interesting. When we read this, we see what it might look like to you as it's saying the absolute value of v equals the square root of x2 minus x1 squared plus y2 minus y1 squared. That's not exactly what it's saying, and I really don't like that this is the way it is. I wish it was something different, and there is some good reason as to why they chose this, but using what they've done is they've turned the absolute value function, this absolute value, these two lines, into something that means something other than absolute value. Up to this point, you're used to seeing these as meaning absolute value. From now on, when you're dealing with vectors, when you see that, think magnitude. So we don't say the absolute value of v equals the square root of all this stuff. We say the magnitude of v, equals all that stuff, the square root of all of that. And that's really what we're getting at. Square root of x2 minus x1 squared plus y2 minus y1 squared. That's all we're saying. The magnitude of v. So keep that in your mind. It's not absolute value anymore. It's magnitude. Again, I don't need to get too much into why that is. But that's it. So with that, that's all the understanding you need in order to jump into these lessons, or 6.1. From here on out, I'll make another video with sample problems that you'll see for homework, and I'll work on them with you. If you have any more questions about how to do these problems, or what to do, how to make it work in your head, I'm more than happy to walk through the problems with you personally. Again, feel free to spam that button that says ask the teacher a question when you get to certain problems, because I'd be happy to help you however I can. So with that said, good luck. I hope this serves you well.